Welcome to the final video in this short series exploring the structure of the atom. In the previous videos, linked in the description below, we saw that the development of atomic theory, starting with the concept of the atom itself 2,500 years ago, had led to quantum mechanics, where, for introduction, the state of an electron was described by four quantum numbers: n, giving its distance from the nucleus; L, the shape of its orbit; m sub L, the direction in which that orbit was moving; and m sub S, the spin of the electron. We further saw that thanks to the Pauli exclusion principle, the periodic table could be read using the quantum numbers. Pauli said that because the last quantum number, that no two electrons could have the same four quantum numbers. Since there are only two possible values for the last quantum number, that means there's only two electrons per orbital, which gives the structure to the periodic table and allows one to easily read that to find the electron configuration. In terms of reactivity, there is another point to consider in the distribution of electrons. The Pauli exclusion principle tells you how many electrons are in an orbit. It doesn't tell you where they are. There is another concept called Hund's rule, which says that as those electrons are distributed, either full or half-full orbits are going to be the most stable. As a consequence of this, two things occur. No orbital can get two electrons in a level until each one gets at least one. This allows one to construct what's called an orbital diagram, the construction of which will be shown in this video. And it will also be shown how this indicates how individual atoms will react. For starters, periodic tables laid out in rows and columns, where the rows indicate what the primary energy level is of the final electron, n, and the columns correspond to which orbit the electron is going into. Two columns on the left indicate the two s orbits being filled, 6 on the right, the 6p orbits being filled, 10 in the middle, the 10d orbits being filled. That final row, it was shown in previous videos, are called the noble gases. They are called noble because they end the row, and therefore they have full shells and do not either want to add or take away an electron. So, we learned previously, if I look at nitrogen being in the second row, that would be helium, 2s2, 2p3. There are 3p orbitals, so according to Pauli, each electron goes in 1, 2, and 3. Again, for review, for a p orbit, the quantum number L equals 1, giving m sub L minus 1, 0, or plus 1, 3 possibilities, 3 orbitals. Oxygen adds one more electron, becomes helium 2s2, 2p4. So the electrons go in 1, 2, and 3. Question remains, where does that fourth electron go? There are only 3 orbitals, so there's no place else for the electron to go except to the next level. If the first 3 electrons are pointing up, that last electron is going to go in and start filling in, pointing down. Similarly, fluorine at 2s2, 2p5 is going to have 3 electrons pointing up, 2 electrons pointing down. Neon, the noble gas, demonstrates in the orbital diagram why it is noble. 2p6 leaves 3 electrons up, 3 down, and no room for any further electrons. An interesting thing happens when one gets to two elements, or 2 columns of elements rather, in the transition metals. If one looks at chromium, one would assume it's in the fourth row, 4s2, n minus 1, 3d, 4 boxes over. If one looks at the orbital diagram, that leaves the s level full and the d level with 4 electrons and 1 orbital completely full. Closer examination shows chromium has 6 electrons and 6 orbitals. So according to Hund's rule, it is much more stable if it reconfigures itself instead of being 4s2, 3d4, to become 4s1, 3d5. This leads to 1 electron in the s, 5 electrons in the d level, and as you note from the picture, each one of these levels is now half full. This is one exception on the periodic table that should be noted. Chromium and the elements underneath it, molybdenum, tungsten, and cygnorium, instead of being S1, S2 rather D4, always rearrange themselves to be NS1, N-1, D5, therefore providing 2 half-filled orbitals in accordance with Hund's rule. Similarly, if one looks at copper, the periodic table reads that it should be 4s2, 3d9. This leads to a full s level, but a d level with 9 electrons that is neither full nor half full. This one is harder to see, which is what makes the orbital diagram so valuable. I now have 11 electrons and only 6 orbitals. However, those orbitals are divided to 1 for the s level and 5 for the d. So copper redistributes itself once again to be, instead of argon 4s2, 3d9, to being argon 4s1, 3d10. Looking at the orbital diagram, this gives you a half-filled s orbit, which is stable, and a completely filled d orbit, which is also stable. Again, this is an exception on the periodic table that should be noted. Copper, silver, and gold, all of the elements that should be S2, D9, will rearrange themselves to S1, D10 in order to fulfill Hund's rule. The periodic table and Hund's rules also tell you how things will behave when they react. The simplest type of reaction is between ions, positive charges, that attract each other. In this regard, looking at the periodic table, actually an older view is simpler. Originally, the way the periodic table was laid out, the S-filling columns and the P-filling columns were called the main group elements, with the central columns in the middle called the transition elements. As such, the periodic table used to be numbered, columns 1, 2, 3, 4, 5, 6, 7, and 8 in Roman numerals on the main group. In this, group 8 are the noble gases. As shown with the orbital diagrams, they are unreactive and they are stable because all of the orbitals are completely full. They have no incentive to either give away electrons or gain electrons in order to gain stability. How does this help reading the rest of the periodic table? If one moves next to group 8, which is group 7, fluorine, chlorine, bromine, and iodine are called the halogens. Fluorine is 2s2, 2p5. If I add an electron, that becomes 2s2, 2p6, which is the same as neon. Therefore, group 7 being 1 away from group 8, every element in group 7 is going to take an extra electron, it will form an anion, and all of them form anions with charges of -1. Next to group 7, you have group 6. which were called the chalcogens: oxygen, sulfur, selenium, fluorine, polonium. Oxygen, 2s2, 2p4, takes 2 electrons and becomes 2p6, or again, the electron configuration of neon. Since group 6 is 2 away from group 8, every single element in group 6 will form an anion, a stable anion, with a charge of -2. The point of ionization is actually to get to the nearest, not the next noble gas. So if I move to the other side of the periodic table, the alkalines in group 1, you'll note sodium is neon 3s1. It is simpler in this case to move backwards by taking away an electron. Instead of moving all the way forwards to argon, a sodium with a +1 again has the electron configuration of neon, which is why everything in group 1, the alkalines, will form a cation with a charge of +1. Similarly, group 2, the alkaline earths. It is much easier to move back 2 than forward 6 to get to a noble gas. So magnesium, neon 3s2, loses 2 electrons, becomes Mg2+, gets the electron configuration of neon, and sets the trend for all of group 2. All of the alkaline earths will react to form cations with a charge of +2 because that brings them back to the next nearest noble gas. The whole point of reacting is for a element to get to a noble gas electron configuration. For groups 6 and 7, gaining electrons and moving forward is the shortest path. For groups 1 and 2, losing electrons and moving backwards is the shortest path. In the middle, groups 3, 4, and 5 have no impetus to either move forwards or backwards, so you will see later that instead of forming ions, these elements are going to share electrons between themselves and form a different kind of bond in order to get a noble gas configuration. The transition metals also form a different set of conditions that must be remembered. If one recalls from previous videos, when filling in the electrons, for the larger elements, between the 3rd level and the 4th level, something odd happens. Filling from the bottom up, energetically, 3s and 3p fill, but the next orbit that comes into play is the 4s level before one hits the 3d. This is why the transition metals are always one row behind. So vanadium is going to have an electron configuration of argon, the last noble gas, 4s2, but 3d3. However, ionization is based on the last in being the first out. Again, referring to the diagram, it's quite obvious that 4 is greater than 3, so if I form vanadium 2+, the 4s electrons will leave first, leaving me with 3d3. Only after the s electrons leave do the d's come into play. So vanadium 3+ loses the 4s electrons plus one of the d electrons to become 3d2. This is why every transition metal has a stable +2 ionization state, because those 2 s electrons will always leave before anything else. And this is the end of this short series on how to use the periodic table. In this final video, you saw how reading the periodic table can help predict ionic bonding, with again group 1 being +1, group 2 always being +2, group 6 always being -2, and group 7 always being -1. In the next series of videos, which again are linked in the description below, we begin to look at bonding and reactivity and different ways that molecules are formed based on the material you find in the periodic table. I hope you find these interesting and useful, and thank you for listening.